All right, welcome to Chapter 3. Chapter 3 means you got through chapters 1 and 2, and you deserve a certificate. A certificate, that's right. We're going to give you I should say you're going to have to print out for yourself a periodic table. And the periodic table we're going to give you, right, we're going to want you to look at and reference all the time. This is it, so it's not like it's, the one that you're going to print out that's on the page for our home page for you to print out looks just like this. But we're going to give it to you, and we want you to always have it with you moving forward in this class, okay? So when you come to listen to the lectures, make sure you have your periodic table. Make sure that you print it out. Hopefully, it is big enough for you. If you find that this isn't, the one that you print out isn't big enough for your eyes, got to find some other way to get it bigger for yourself. And, mostly the material on other periodic tables online are just fine. On the back of the periodic table, you're going to see some tables, which are also very critical. It's best if you have the periodic table printed out front and back, or at least both of these pages together all the time. We'll get into these tables later on throughout the course, okay? So congratulations, and please print out your certificate for you and have it with you throughout the class. All right, so we're going to start talking about, how have you been, Fred?
I've been fine.
Oh, you have a different voice today. What happened?
Yeah, I had a major surgery.
What? What do you mean?
Yeah, they took my tonsils out, and so I have a little bit of a different voice, but my mind's as sharp as ever.
Oh, that's good. Good. Great. Great to hear. Okay, so moving forward then, we're going to introduce, or not introduce, you guys already know about elements and compounds and the periodic table a little bit, but we're going to go in more in depth in these ideas, okay? Let's first make sure we are aware of the 3 different subatomic particles. You know what subatomic means?
Yes, it means subatomic, smaller than the atom.
That's right, subatomic. So we're looking at these 3 different subatomic particles, electron, proton, and neutron. And which 2 of these are in the nucleus?
Protons and neutrons are in the nucleus.
That's right, protons and neutrons are in the nucleus. Now, we most likely know that electrons have a negative charge, protons have a positive charge, and neutrons are not charged, right? But we might not know the relationship between the masses of the protons and the electron, all right? And this is what I want us to pay attention to here. You see protons, 1.67 times 10 to the negative 24th grams, compared to electrons, 9.1 times 10 to the minus 28, right? Electrons are about 1,000 times smaller than protons. So that's something important to keep in mind, okay? We have elemental symbols, and we've already kind of discussed these elemental symbols a little bit. But now I'm going to discuss with you a way to convey to people through your writing of elemental symbols information about the number of protons and the number of neutrons and the number of electrons on a given atom, okay? So, for example, here is the hydrogen atom. Now, do you remember how many protons hydrogen has?
I think I do, but do you have the periodic table there?
Yeah, right. You can always tell by looking at
1.
Right, you can always tell by looking at the periodic table. It has 1 proton, right? Because that number on the periodic table tells us how many protons are in that kind of element. Excellent, that number. So, another way you can do that for people who might not have the periodic table nearby, and this is really for the olden days, is they would write a subscript number in front that would represent the number of protons in that element. So carbon here would have a little 6 down there because 6 is the number of protons that carbon has, right? The number of protons that carbon has. Okay, so it's kind of redundant because we are always going to have a periodic table around us, right? And if we're not, we have a phone, we have Google. We're never going to be on the desert island. That's not the idea here. So we're always going to have that periodic table with us, and so you'll see you won't see this as frequently, okay? But remember, it's the number of protons, okay? Now, up here, a superscripted number right there, that's a little bit more informative, and it will be specific to whatever element that we're drawing or writing up, whatever element we're talking about. And in this case, the 12 means the number of subatomic particles that are in the nucleus, or the subatomic particles that are contributing to the mass. And therefore, we call it the mass number, So 12 is telling us how many protons plus neutrons we have. So for example, here's some element right down here. It tells us the number of, what was that one down there?
Protons.
That's right, number of protons. And up here, right, that tells us the number of protons plus neutrons, okay? This is just the number of protons down there. Now, can you tell what element this is just by looking at what I've drawn so far?
I could if I had the periodic table by me. I don't have it right now.
Oh yeah, okay. So if we look at our periodic table, we can tell how? What are we looking for now when I look at the periodic table?
Just looking for which one has 7 protons. It's nitrogen. Nitrogen has 7 protons. There's a 7 down there. So that's how many? That's nitrogen.
All right, great. So what does the 15 mean?
Well, it's telling us that 15 protons plus neutrons, so that means you might have another 8 neutrons in there. So you got 7 protons, 8 neutrons.
Right, very good, excellent. Okay, so the lower number tells us the number of protons. The upper number is the mass number, and it's the protons plus neutrons. Excellent. Now, on the periodic table itself, below the number, and it's usually, but no, not all periodic tables are organized exactly the same way, and they don't need to be. But the number that is, not a whole number, 55.847, for example, that is the average mass of an atom of iron. The average mass, because the different elements that are out there, if we use iron for an example, all the different iron atoms that are out there, they all have differing number, or they could have differing numbers of neutrons in their nucleus.
They can have different number of protons, right?
That's right, that's right. If they're iron, they have to have how many protons in the nucleus?
Do you have the period? Oh, well, I guess it says right there, 26.
That's right, we have it right here in front of us, 26. But that's right, if it's iron, it's always going to have 26 protons, okay? So, 26 protons, 55.847 is the average mass.
So some weigh 54.5, some weigh 56, maybe some 57, 54, like that?
Yeah, that's right. And now why do any of them weigh 26?
I don't know.
Well, probably not, right? Because, we actually know, because there has to be some neutrons within the nucleus as well.
Always?
Well, not always, but for something, as nuclei get larger, more protons in them, then yes, you need to have a number of neutrons. And generally, it's almost a 1-to-1 ratio. As you get larger, it diminishes and it's less than 1-to-1. But there's usually about 1-to-1, 1 neutron for every proton. So this is the average mass. And remember, you take the average by adding up all the different masses of the, in this case, iron atoms, and then dividing by how many you added up, and that gives you the average. Now, if I have 2 kinds of elements portrayed, for example, here, I'm looking at this carbon and this carbon, and we call the element carbon 12 after the mass number. We never would call it carbon 6, because carbon 6 just tells you how many protons there are. And we're already calling it carbon, so we know how many protons there are.
If you have a periodic table.
That's right. That's right, and that's what we're kind of relying on. So when we do say something like carbon 14, the 14 is referring to what?
The number of protons and neutrons in the nucleus.
That's right, the number of protons and neutrons in the nucleus. Or what's the other name for that?
The mass number.
That's right, the mass number. So when we have two different elements, two different atoms that have the same number of protons, that means they're the same kind of atom, but they differ in the number of neutrons. They'll have a different mass number. We call those isotopes. And this is kind of an important thing to remember. There's so many different things you can learn from the different kinds and the ratios of different isotopes in elements. So it becomes a very important thing, not just for chemistry. Okay. Chemically, isotopes are virtually identical, right? There's very few chemical reactions that we really examine with different isotopes to kind of learn about them. Right? It is something we do, but it's not a huge portion of the chemistry that occurs. Okay, so let's move on here. Now, here's an example again. Our elemental symbol, Z, is the number of protons. A is the mass number of neutrons plus protons. Okay, so looking at this, we have neon here. Can you tell me how many protons neon has?
10.
That's right. And then what does the 20 tell us?
You could tell that it has 10 neutrons as well.
That's right, 10 neutrons as well, because 20 is the sum between the protons and the neutrons. Okay, so let's see if we can fill out this chart. Let's see. What would we call this one? Do you remember?
Cobalt.
Very good, cobalt. How did you know that?
Oh, I used to work with some people. What was that?
Oh, sorry about that. I don't know.
I used to work with some people that they use cobalt a lot.
Oh, okay, great. So, cobalt, and now what is the 60 telling us?
It's the mass number, or the number of protons plus neutrons.
Very good. Do you know how many protons are in a unit of cobalt 60, an atom of cobalt 60?
No, but if you show me the periodic table, I can figure it out.
Okay, there we go. Cobalt, you see it?
Yeah, it's number 27.
All right, so how many protons?
It has 27 protons.
Okay, very good, 27 protons. Therefore, how many neutrons is this going to have?
33.
That's right, 33 neutrons. Very good. That's just the 60 minus the
27.
That's right, good. All right, now what about electrons?
You didn't tell us about electrons.
Yeah, you're right. But I did tell us last class, remember when we said that unless there is a charge on the species, on the atom, whatever it is, if there's not a charge, and the charge would show up here, I didn't really talk to you about that, but there is no charge here. So that means the number of protons is the same as the number of electrons is the same as the number of protons.
Oh, yeah, I remember that. So 27.
Yeah, that's right, 27 electrons. Very good. All right, I'll keep the periodic table right here. Can you figure out this one?
Bromine 81, protons, let's see, which one's bromine? There it is, 35.
35 protons, very good. How about neutrons?
What's 81 minus 35? Is it 36? No, 46.
Okay, good job. How about number of electrons?
35.
That's right. How did you know?
Because there's no charge. No charge means it has the same protons as electrons.
Excellent job. All right, looking at this species we have to fill in here, what do we know about it?
Well, it must be 29, 26. It must be copper because it has 29 protons.
That's right. Copper has 29 protons down here and 29 electrons, no charge. So are we going to call it copper 29?
No, you're going to call it copper 29 plus 36. So 54, 64, copper 64? Oh, 65. Oh, sorry about that. Okay, good. 29 plus 36, 65, right? Copper 65. So 65 is the sum between the protons and neutrons. All right, excellent job. How about this one? An atom of Pb, that's lead. I always remember that because Pb sounds like plumber, and they come from the same root there, right?
has how many protons, how many neutrons, and how many electrons?
It has to have 82 protons and 82 electrons, so I'm going to have to go with D.
Oh, very good. That was a good job. Excellent job. All right. How many neutrons are there in iron 52?
Iron 52. Now, what is that 55.847 again?
That is the average mass of all the iron atoms. So this is only helpful here because it's showing us again that iron has 26, what is that?
Protons.
Yeah, 26 protons, okay? So the neutrons are going to have to be identified by using this number, 52. But does it have 52 neutrons?
No, that's the sum. So 26 plus 26 is 52. So I guess it has the same number of protons as neutrons.
That's right. Very good. So 26 is our answer, C. Okay. Now, let's think about how we could answer a problem like this. Naturally occurring chlorine is a mixture of two isotopes. Do you know what that means, a mixture of two isotopes?
Let's see. Isotopes mean same number of protons, different number of neutrons. So if there's two isotopes, that means some have one amount of neutrons and the other amount of neutrons. How many protons does chlorine have?
That's a good question. Let's see. Chlorine, there's 17, right? 17 protons. So when we say chlorine 35, that means that 35 minus 17, right, is the number of neutrons for chlorine 35. But for chlorine 37, 37 minus 17, so we got 20 here and 18 neutrons in chlorine 35. Now, we're being told here that naturally occurring chlorine is a mixture of two isotopes, and in every sample of this element, 75.77% of the atoms are chlorine 35, and 24.23% are chlorine 37. And then the question is, and it also gives us the exact mass of the chlorine 35 atoms and the exact mass of the chlorine 37 atoms. And then we're supposed to calculate the average atomic mass of the chlorine. So what would we do?
Well, we'd probably take the mass for the chlorine 35, 34.9689, add it to the mass of the chlorine 37, 36.9659, and then just divide by 2 and you'll get the average.
Okay, that would be the case if I only had two atoms, right? If one was 35 and one was 36.
Didn't you say you just had two isotopes?
Yeah, it says I just have two isotopes, but that doesn't tell me that doesn't mean that half and half or 50% are one and 50% of the other, right?
Oh, yeah. So it's saying 75.77% are the chlorine 35. So I'm not really sure how to do this.
All right, so what we would do is we would take our 75.77. Whoops. Let's get this a little bit smaller. We take our 75.77 and think of that, because it's a percentage, it's out of 100. So we would think of that as how many atoms would have 35, the mass of 35, or in this case 34.9689. So that many would have 34.9689. And so instead of, if you pulled 100 atoms out of a hat, 75.77 would have that mass. And so you could add up 75.77. No, sorry, you could add up 34.9689, 75.77 times if you were going to take the average, but instead we'll just multiply it by it. And then we add it to our other percentage, 24.23%, right? This is the first percentage. And multiply that by the, what's our other number?
36.9659.
Okay, very good. So that is telling us that if you pull 100 atoms out of a hat, that's how many will have this mass, and that's how many will have that mass. So now we just have to divide that by how many times we pulled the atom out of the hat, which is going to be 100, and that will give us the mass of the average mass of the nucleus of an atom of chlorine. Okay, so hopefully we can do that in our calculator and get 35.45. So again, this isn't just 50% 50% 37 and 50% 35, right? And so you can't just add the two together and divide by 2. Okay, here's another one. 2 isotopes of element Z. The first is 56.5% in abundance and has a mass of 152.3. And if the atomic mass is 155.5, what is the mass of the other isotope? Okay, so this is like the other question, but what's different?
Well, we need to find the mass of the other isotope, but we don't know the average. What's the average mass?
Well, when they say the atomic mass is 155.5, that's the average mass. That's the average mass. So you're right. We can set it up the exact same way, but we just need to have our 155.5 as our average here, and then we set it up and find the unknowns there. So what do we do here?
Well, you take the 56.5% and you multiply it by the 152.3.
Like that?
Yeah.
And now what's the other part?
It says 56.5%. Okay, so it doesn't say that the percentage of the other one, but it only says there's 2. So therefore, it's got to be a sum of 100%, right? So let's see, 56.5 minus 100, right?
All right, is that 44.5? Is that right? Let's see. So 43.5%, that's the rest there. Now we multiply this by what?
I don't see it. I'm not sure.
Well, that's what we don't know, right? That's what they're asking us. They're asking us the mass of the other one. So we'll put that as our x. Now, do I have to divide this by something?
Yeah, we needed 100 down there.
That's right, because this is out of 100 samples. That's right. Okay, so putting that in the calculator, hopefully we get the number 159.7. And again, what is that?
That's the mass of the other isotope.
That's right. Very good. Excellent. Okay, very good. So we have to be able to remember isotopes. Here is another type of problem that you kind of have to be understanding. An element has an atomic mass of 15.987. The mass of one of the isotopes, X, is 15, and the mass of the only other isotope is 16. So what does that mean about the natural abundance of the isotope?
What does natural abundance mean?
Natural abundance, that's good. That's our fancy little phrase we use when we're talking about how much in nature of the atoms that exist are either of one isotope or the other. Okay, so there's 2 different isotopes. What are their masses?
15 and 16.
That's right, 2 different isotopes, 15 and 16. And we know that the atomic mass is 15.987, and that's essentially saying the average mass of an element out there is 15.987. So why isn't the average mass just 15 plus 16 divided by 2? Why isn't it 15 and a half?
Well, because they're not half and half. It's not half 15 and half 16. So the average mass is 15.987. That means that the average mass is, most of the isotopes are closer to 16. That's why the average is so high. It's 15.987.
That's right. Most closer to 16. So what does that mean?
Well, it looks like the abundance of X is less than that of Y.
Okay, so there's less 15 than there is 16. So you're saying the answer is C.
Yeah.
Okay, very good. Good job. All right, so the periodic table was initially recognized to be of importance when people began to realize that there were trends within elements. For example, the periodic table, the way we look at it now, right? I showed you how sodium, remember when we mixed sodium, put a little piece of sodium in the water in that video?
Yeah.
What happened to it?
It blew up.
That's right, it blew up. Well, guess what? If you put potassium in water, it will make an even larger explosion. And if you put rubidium and cesium in water, it will also make a larger explosion. And they began to realize this, that elements behaved similar to each other for certain groups, families behaved similar to each other. And that when they began to order them into a table, then these similar properties would be able to be recognizable and predictable. Okay, and Dmitri Mendeleev was credited for this because he put different elements into little tables like this and began to be able to predict the properties of the elements based on where he had them. And he was, as people began to discover new elements and also identify properties of new elements, which were just like he predicted, he became very popular and kind of became known as the father of the periodic table. All right, so the periodic table is organized into rows, which we call periods, and groups, which we call families. And some families are a little more popular than other families, okay? And I will tell you the names of some of these families that we want to remember, but we don't need to remember all of them. But we do want to recognize that families have different properties that are similar to each other, right? As we mentioned. All right. The periodic table also is kind of segmented into little sections, which we want to become familiar with. All right. For our periodic table, our blue, what do we got here? Our blue, wrong way. Okay, there we go. Our blue section here is our transition metals, our transition elements or transition metals, because they are all metal. Okay. Whereas our 2 columns at the beginning and our 6 columns at the end are called our representative elements. And that's because there are certain rules that are in chemistry that are followed really well by the representative elements. Not so much by the transition metals and the intertransition metals always. And so we call these the representative elements, and often we'll refer to the representative elements when we're talking about when we're learning the rules of chemistry, because they follow them very well. We have our first row here, 1A, which is our first row here, and they're called the alkali metals. Our second row is called the alkaline, wait a second. Oh, sorry, the alkaline earth. So this alkaline earth is supposed to go over here with this. Second column here is alkaline earth metals. Our 7th column over here are our halogens, and our 8th column are our noble gases.
How do you get 8?
Oh, 8, we say 1, 2, 3, 4, 5, 6, 7, 8 when we're referring to our representative elements. Okay? Let's see. And here is our periodic table, our alkali metals again, alkaline earths, our halogens over here, and our noble gases. Okay? And again, this staircase, do you remember what that staircase does?
It separates the metals from the nonmetals. The metals are on the left and the nonmetals are on the right.
Very good. Excellent job. Now, the modern periodic table should be sprawled out like this, except that it doesn't fit very good on an 8.5 piece of paper. And so we, pictures of my son, sorry about that. So this...
he's a nice guy.
Yeah, he is. He's a nice guy. So the modern periodic table to fit on an 8.5 by 11 looks like this, but really it would be sprawled out like this. All right. And this just emphasizes our metals and our nonmetals. And then also, we haven't talked much about the metalloids, or the elements right along the staircase, except for aluminum. Aluminum is a metal. but again, some very similar properties relative to or compared to its neighbors, right? And so anywhere you go on the periodic table, their neighbors will have relatively similar properties to them. Okay, now your turn. Which of the following is correct? Copper is a representative element, sodium is an alkaline earth metal, carbon is semi-metal, fluorine is a halogen, or are none of these correct?
Could you bring up the periodic table so I can see?
Yeah, there you go. Okay, so here's our periodic table. What do you think?
Copper is what number?
Number 29.
Yeah, so that's what do you call it? What did you call those?
Those are transition metals.
Okay, so that's a transition metals. So A is not right. Na, sodium, right?
Yeah, so like sodium chloride.
Where's it?
It's number 11.
Okay, so that's an alkali. That was an alkali earth. Alkali earth was the second. That's an alkali metal, so B is not correct. C, let's see. Carbon isn't on the staircase. It's not a semi-metal. It's a non-metal. So D is D, right? F is a halogen. Where's F at?
It's number 9 over here.
F, that last row, I can't remember, what was those called?
Let's go back and take a look here.
Oh yeah, F are the halogens. So that's right. That one's good.
Okay, very good. So, fluorine is a halogen is our correct answer. Very good. So, let's think about some properties of metal. Most of these properties are properties you're familiar with. They are shiny. They reflect light, right? They're shiny. They're conductive. They conduct the electricity and heat. I don't know if you've done it much cooking.
Yeah, I cook.
Okay, so you know how pans get hot faster than a ceramic material like plates, right? Okay, so they're all solids at room temperature except for mercury. That's an exception, right? Malleable and ductile. Let's take a look at this video here of this person cutting up a piece of sodium metal.
That's sodium metal?
Yeah, that's sodium metal right there. They're cutting it up with like a chisel. And see, it's not terribly hard. Kind of like a piece of clay almost, right? So metals are generally malleable like this. Now, when we think of metals, we think of chair legs and door frames and stuff like that, which are metals, but they're usually alloys, combinations of metals. And when you combine metals together like that, you get different properties, and they become much more hard, much more durable. In fact, that's why jewelry is generally not made out of a single metal like gold. So he got off a chunk of sodium here, and he's putting the rest into that container. That container prevents the sodium from interacting with the water. See how it has a white haze along the edge?
Yeah.
That white haze is from the oxygen in the atmosphere interacting with, and the water in the atmosphere interacting with the sodium metal. All right, here's another video of sodium being dropped into water.
Oh, I know what's going to happen.
What's going to happen?
It's going to explode.
That's right. So let's take a look here. Good snap.
Where's it at? That looks like a firework.
Yeah, you're right. It is a very similar principle. Fireworks usually contain metals. Yeah, that's right. So, we're going to watch another video here of people not putting sodium into water, but putting rubidium and cesium into water. Okay? So, my goodness, why is that doing that today? So, we're going to look and see rubidium and cesium being placed into water by this oops, over here. Oops, this one here. There it is.
Back and watch the mayhem. And that's just what we're going to do. Mr. Tickle, bring on the rubidium.
Here it is.
Is that it?
Well, it might not look like much, Richard, but it's a highly reactive metal. It's sealed in this glass tube under argon atmosphere conditions, just for safety.
Right, so what's going to happen when you drop that in the water?
Well, imagine, if you will, letting off a hand grenade in a bathtub.
Righto, I'm off. Have that.
Okay.
Good luck. Okay, Tickle. Drop the rubidium in the water.
Stand back, everybody, this one's going to be bad.
2 grams of rubidium will only react when our specially designed vial dissolves in the water, which gives John a few crucial seconds to get into our safety zone.
That is more like it. Only on Brainiac do you get that kind of science.
But I believe we can go one better. There is one more alkali metal we can legally use.
Yes, Richard, cesium, the emperor of alkali metals, particularly nasty, could go off at any time.
And that's it.
Oh, yes.
Brilliant. I like it already. Now, what's that going to do when it hits the water?
Imagine a depth charge in a bathtub.
Fair enough, mate. I'll leave it to it. Good luck.
Thank you.
Okay, John, go for it.
Warning, 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 extreme danger, clear the area.
As our cesium sinks in the water, the rapid generation of hydrogen gas should produce quite an explosion. And it does.
All right. So what we see there is the property principle, right? Where within a given column, the elements have very similar reactivities. They are reacting very similar to each other. All right. So some properties of metals. Nonmetals. Nonmetals. Now, this doesn't mean all metals are explosive. We learned a couple of different things there, but nonmetals. Nonmetals to the right of the periodic table, right? Not malleable, not conductive. Most are solids or gases. Again, only one is a liquid.
Which one's a liquid?
Oh, bromine. Bromine is the only liquid. At room temperature, all materials can become solid, liquid, or gas, depending on their temperature, right? So at room temperature, we really only have mercury as the element that's liquid and bromine as an element that are liquid. Okay? Metalloids have a property, very interesting, semiconductors. They can be semiconductors, meaning that with a charge, they will have more metallic-like properties, whereas in the absence of a charge, they become more non-metallic, non-metal-like. So, very important contributors to computers and storing data initially, right? So we learned a lot from these properties and materials. And now they're playing a big role in photovoltaics or solar panels, right? Okay, so now I'd like to introduce you to the idea of an ion, or atom that does not have the same number of electrons as it has protons.
Oh yeah, you mentioned that.
That's right. We talked about this a little bit before. That an atom, if it has a differing number of electrons than it has protons, it will have a charge. All right? And we call these kinds of species, it's not really called an atom anymore after it's got a charge. It becomes what we call an ion. And we show the ion with a charge. So, for example, if I have an atom of sodium, there's my atom of sodium. How many protons? How many electrons?
11 protons.
Right there it is, 11 protons. And without a charge, then how many electrons?
Also 11 electrons.
That's right, 11 electrons. So, if I have 11 protons, 11 electrons, and then I lose an electron.
Then you only have 10 electrons.
That's right, I only have 10 electrons, but I still have the same number of protons. So now with 10 electrons, only 10 electrons and 11 protons, the result is going to be a positive charge. So I lost my electron and I result in a positive charge. Now some people get bothered by that. They think that the positive means plus an electron, all right? Because that's what happens in chemistry. We either gain or lose electrons. But the positive charge just means that there's one fewer electron. So it doesn't mean plus adding an electron. It means the resulting charge is a positive charge. Okay? And now we call this a sodium, same thing, it's sodium metal. Now we call it a sodium ion if it has a charge. Very good. Chlorine over here, if it gains an electron, for example, here's chlorine. If it gains an electron, then it has what we call a negative charge because it has one extra electron. If this chlorine species, which has gained an electron, how many electrons does it have now? If it started with, how many did it start with?
Chlorine atoms have 17 electrons if they don't have a charge. So if they have -1, that's one extra electron, that's 18 electrons.
That's right. That's right. So this chlorine atom now has an extra electron, and nonmetals, when they gain an electron or become ions, they are not called chlorine ions, they're called chloride ions. Chloride ions. So metals, just call them sodium, same name of the metal, ions, but these ones we end now in "ide", not the way the normal element name would end. We also have general names for positively charged ions and negatively charged ions. Positively charged ions are called cations, and negatively charged ions are called anions. So, I have a joke for you. Do you like jokes?
Yeah, I like jokes.
All right, so here's the joke. It's not a very good joke, so be ready.
Okay.
A dog walks into a restaurant and says to the cat, "How are you?" And the cat says, "I'm fine." And the cat says, "I think, though, that I'm sick." And the dog says, "Are you sure?" And the cat says, "I'm positive."
Then what?
That's it. That's the joke.
That's it?
Yeah, that was it.
That's not a good joke.
No, it's not a very good joke, no. But the idea is it's going to help you remember that cat was positive and that cations are the positively charged ions.
That's not a good joke. I would get rid of that joke if I were you.
Well, that's all right. It's okay. I'm not concerned whether it's a totally good joke or not. I just want you to be able to remember cations are positive.
Okay.
And now, too bad the negatively charged ones aren't dog ions, but they're called anions. Okay? So now we have to remember cations and anions. Cations being positively charged, anions being negatively charged. Now, when I bring different ions together, and what would this ion be called?
Fe, that's, what is it again? There we go, yeah. It's iron. So that is an iron.
That's right. And what is this one called?
That's oxygen atom, oxide. Oxide, like chlorine goes to chloride, so oxygen goes to oxide. Is that right?
That's right. So we have an iron atom and an oxide atom. Iron ion and an
Oxide ion.
That's right, oxide ion. Okay, very good. Now, I'm going to bring these together, and they're going to form a compound. Now, the iron ion, it let go of its electrons and gave them to the oxygen atom. That's where the electrons went. The oxide ion gained those electrons from the iron. So it couldn't have occurred by just one atom of iron losing 3 electrons, because one oxide ion only received 2 electrons. So what we can see here is that if we're going to, oh man, why does it keep doing that? If we're going to combine iron ion, Fe plus 3, with an oxide ion, the number of electrons that are lost by the cation have to be the same number as gained by the anion. So what that means is that I'm going to have another oxide ion, but when I do that, I realize that now I've lost 3 and gained 4, so I'm going to need another iron ion, and then I'm going to have another oxide ion. Okay, so by looking at my ions that I start with, I can see that I'm going to need how many of each I'm going to need to have them come together to form a compound. And the resulting compound that will be formed is Fe2, because there's 2 iron ions necessary, O3. Fe2O3. Very good. And this compound is called an ionic compound. I don't know if you remember, but we said that one way that we could recognize ionic compounds are by whether or not the compound contains a metal or not, because ionic compounds almost always will contain metals. But I did also say that the best definition for an ionic compound is a compound made of ions. And now we know what ions are. Okay? So, those are our ionic compounds. Okay? And we can tell what kinds of ratio ions will come together in by understanding the need to balance these charges. Well, we'll get to that in a bit. All right, so how does calcium form a calcium +2 ion? What happens when calcium forms a +2 ion?
You said +2 means, what did you say? You said +2 doesn't mean getting 2 electrons, right?
That's right. +2 doesn't mean it's gained 2 electrons. +2 is the resulting charge because of something that happened. And why would it have a positive charge?
Because it has 2 fewer electrons. It doesn't lose protons, it can only lose electrons or gain electrons.
That's right. So for calcium to become a calcium ion, a calcium atom to become a calcium ion, what has to occur there?
It has to lose 2 electrons.
That's right, it has to lose 2 electrons. Very good. What about nitrogen? How does nitrogen form an N3-?
Oh, yeah, to get 3 minuses, you had to gain 3 electrons.
That's right. That's why you'd have an extra 3- charges, because you've gained 3 electrons. Very good. Now, here's our classic example, which we will refer to frequently, where we think of sodium metal and chlorine gas coming together to form a compound. And I'll show you this video here as we talk about what sodium and chlorine, why they like to come together. So that's a piece of sodium metal at the end of that straw. And the gas inside that flask is chlorine gas. At the bottom of the flask, there's a little bit of sand. And that sand is going to prevent the glass from cracking from the reaction, the heat of the reaction. Nothing occurs initially, and we need to overcome a little bit of activation energy, which we'll talk about in Chem 106. But we add a little bit of water, and the water hits the sodium and reacts like we know it's going to, but then the chlorine gas gets involved, and we get the formation of this haze, which is a solid smoke, right? Smoke is little bits of solid floating around, and that solid is our sodium chloride. Okay? So, sodium gives an electron to chlorine, and sodium becomes a positively charged ion. Chlorine becomes chloride, or chlorine atom becomes a chloride ion by taking that electron. And then those 2 ions stick together to form an ionic compound, sodium chloride. Okay? Very good. Now, these ions, ionic compounds, make pure water conductive. If you put salt into pure water, like sodium chloride, the solution becomes conductive, and electricity can then pass through it. It's not that the solution makes electricity, it's just allowing electricity to pass through. And light bulbs can light up, for example, if you provide power, and that's usually our way that we kind of indicate in this class, that a solution conducts electricity by showing that the light bulb has lit up. Pure water does not conduct electricity, but salt in water does.
Now, you said that salt doesn't just mean sodium chloride, right? What else does it mean?
That's right. It also refers to any ionic compound, which is a combination of a metal and a nonmetal. Another indication that ions exist is if you take sodium chloride solid, it's not conductive, but if you melt it and make it a liquid, it will become conductive. Okay? So, ions create conductivity when they're either dissolved or melted, dissolved in water or melted. Now, we have another opportunity to fill in the blanks here with this. Do you remember how many? Let's bring up our periodic table. Whoops. There we go. How many protons does this species have?
Cobalt has 27.
Yep, 27 protons. How about neutrons?
It should be still 33, right?
That's right, 33. Now electrons. What's electrons?
Let's see. Plus 3 charge. So 27, not adding 3, but it means it's lost 3, so 24 electrons.
That's right, 24 electrons. Bromine 81.
35 protons, 46, was it, neutrons? And 36 electrons.
Very good. Excellent job. All right, so our last one here. What was this one?
It was copper 65. It's still going to be copper 65, but what? It's going to have 2 less electrons, so it's going to have a plus 2 charge.
That's right, copper 65 with a plus 2 charge. Very good. All right, so we can also look at the periodic table to identify what the expected charge would be on a given atom if it were to form an ion. For example, calcium. We can find calcium. Look at the periodic table. Do you see it? Where is it at?
It's element 20.
Very good, element 20. Here's calcium. I can look at where it's at on the periodic table, and I can predict what kind of charge it's going to form based on the understanding that our final column here is our column of what we call our noble gases. Now, there's a reason we call them noble gases. It's because they have the number of electrons that all the other elements want to have. If an element finds itself with the number of electrons that a noble gas has, it finds stability, and we call it a noble gas electron configuration. How many electrons does an atom of sodium have?
Sodium? Atom of sodium has 11 electrons.
That's right. And the nearest noble gas to that is neon with 10 electrons. So sodium finds stability by losing an electron and becoming like an atom of neon in terms of the number of electrons it has. It doesn't lose protons, but it can find stability even if it has the same number of electrons as a noble gas. So calcium can do the same thing. Calcium, how many electrons does it start with?
20.
That's right. And what can it do to find stability?
It has to get either 10, 18, 36. 18 is closest. So to get 18 electrons, if it has 20, it needs to lose 2 electrons.
That's right. That's right. So we can think about calcium and say for it to form an ion, it's going to want to get a plus 2 charge. Does that make sense?
Yeah, and so sodium was just let's see the periodic table again. Sodium is just going to be a plus 1 because it wants to give up 1 electron.
That's right. Excellent. Now nitrogen. What do you think it's going to want to do to form an ion?
Show the periodic table.
Okay, yeah. Here's nitrogen.
Oh, okay. Yeah. So it can lose 1, 2, 3, 4, 5. Plus 5?
Well, yes, it could do that, but what could it do if it were to try to become like neon?
It can't lose electrons to be. It could gain 3 electrons to be like neon.
That's right. That's right. So nitrogen doesn't lose electrons. It's a nonmetal, so it's going to instead gain electrons. And if it can gain 3 electrons, like you said, it can find stability. How about oxygen? What does it want to do to find stability?
Gain 2 electrons. So that's a minus 2 charge.
That's right. Very good. Now let's see. Are you going to remember what do you call, which of these are cations and which are anions?
I remember the joke. Positives are cations, negatives are anions.
Very good. So these are calcium and sodium cations, nitrogen and oxygen, or nitride anion and oxide anion. Very good. So now when we write a ionic compound, we're combining ions together in such a way that the number of electrons that the metal lost is equal to the number of electrons that the non-metal gained. So these charges have to be balanced for the ionic compound to be drawn, or to be written. It's chemical formula, right? So if I'm going to combine an aluminum with an aluminum ion with an oxide ion here, what is the resulting compound's chemical formula going to be?
You're going to need 2 aluminums and 3 oxide ions.
Oh, good. You already figured it out, huh? How did you know that?
Well, if you have -2 and +3, you're going to need to have a least common multiple of 6. So 2 aluminum +3s or 3 oxygen -2s.
Very good. Excellent. Another way to do that is to do this little crisscross rule, where you can use that to kind of help you recognize the resulting combination between those two ions. See how that rule works?
Yeah, I see it.
Okay, good. So now what happens if we want to combine magnesium and oxide?
Well, you can do the crisscross rule, like you said, but it would be Mg2O2. Do you do that, or do you just say MgO?
You're right. You only just say MgO because you always want the expression for an ionic compound. Now, how do we know these are ionic compounds?
Because they contain metals.
That's right. So for ionic compounds, the chemical formula is always the lowest number expression for the number of elements in the compound. All right, so now this is the introduction of a new species. What is this?
I don't know.
This is what we call a polyatomic ion. Polyatomic. Do you think you know what the term polyatomic means?
Poly means many.
That's right. Poly means many. So polyatomic, many what?
Many atomics. Or atoms, many atoms.
That's right. Polyatomic ion means many atoms come together and they still end up having a charge. So this ion, this is called the ammonium ion, and this ion, the phosphate ion, can come together, but we still need to balance out the charges. So how many of these cations are we going to need?
3.
And how many of these anions are we going to need?
Just 1.
That's right. So I can draw this by writing parentheses around them, or around the one that we need more than one of, and putting a 3 there. And the phosphate here just doesn't need a parentheses, it's just 1. Now, we want to recognize that when we have an ionic compound, what it is that we have is, so here we're putting some salt into water, to show that, let's see, right here, this is a better video actually, right, or a little better spot in the video. So when we have an ionic compound, what we have is we have our ions. In this case, we're talking about sodium ions and chloride ions, and they come together in this 3-dimensional lattice, okay? A 3-dimensional lattice means basically that each sodium ion and each chloride ion has neighbors, lots of neighbors, 6 neighbors in this case, of the oppositely charged species, okay? So, that is always the case for ionic compounds. They're in these 3-dimensional lattices, and these numbers down here are telling us the ratio of the different ions to each other in that compound. All right, so which of the following is the correct formula for a unit of potassium and oxide ions? Potassium and oxygen coming together as ions. Okay?
Can I see the periodic table?
Yeah, sure. There we go. Oh, man, it's frustrating. Okay, so here we go. We have potassium. Do you see it?
Yeah, it's element 19.
All right, so potassium is element 19. Oxygen is element 8. So potassium is going to want to have what kind of a charge?
It has 19 electrons. It's going to want to have, closest one is 18, so it's going to want to lose one. Is it safe to say that everything in the first row will always want to lose an electron in an ionic compound?
That's right, yeah. Lithium, sodium, potassium, rubidium, all these, if they're in ionic compounds, they're going to want to lose one electron. And that's also true of the second row. If it's in the second row, it's going to want to lose 2 electrons. That's true for those 2 rows, so that's very good. So potassium is going to want to do what?
Lose 1 electron.
That's right. And oxygen, do you remember what oxygen wants to do?
I can't remember. Let's look. Oxygen has 8. It's going to want 10, so it's going to gain 2 electrons.
That's right. So let's write down what we've learned there. We learned that we have a potassium ion. Potassium wants to gain an electron, and potassium wants to lose an electron, and oxygen wants to gain 2 electrons. So how does that help us know what ratio they want to come together in?
Well, you do the crisscross stuff, and potassium, you're going to need 2 potassiums for every 1 oxygen. So I think that the answer is going to be K2OC.
Okay, very good. Excellent job. Now, we just mentioned that we can identify the charges on ions or atoms that are going to form ions based on their location on the periodic table, especially for this first row and this second row. But for our transition metals, that's just not the case. Their location isn't as easy right now to identify, or doesn't give away, doesn't tell us the kind of charge that those atoms will form. And in most cases, transition metals form more than one kind of ion. Iron, for example, can form a +2 charge or a +3. And we'll gradually become aware of what different metals, different transition metals can and can't form in terms of ions. But I'd rather you not necessarily try to memorize this, but you'll gradually recognize the kinds of ions that can be formed. Okay? All right. So, which of the following is the correct formula for the formula unit composed of an iron +3 ion and sulfide ions?
Sulfide. I don't know what sulfide ions like to do.
All right, so we can look down here on the periodic table. We see sulfur, and we can see that sulfur is 16 electrons. So what kind of a charge is it going to want to form?
-2. So you got an iron with a +3, sulfide with a -2. It's going to be Fe2S3. It's going to be C.
That's right. How did you know that?
Well, the crisscross rule. I just took the 3 from the iron and put it on the S, and the -2 for the sulfur, because sulfur needed 2 electrons. Oh, why does it keep doing that?
I don't know. Sorry about that. Sulfur needs 2 electrons. That's right.
Okay, there we go. And that's -2, so the iron is going to have the 2.
Okay, excellent job. Now, on the back of your periodic table, as we mentioned, there is a list of our most popular, not all of them, but many of them, most popular polyatomic ions. Polyatomic ions. And we want to become familiar with all of these. And if you're good at memorizing, memorize them, because that will help. If you're not good at memorizing, and even if you think you are good at memorizing, what I want you to do is make sure that every time you come to class, just like you bring your periodic table, on the back you want to have this polyatomic ion chart. And what that polyatomic ion chart is going to do is it's going to allow you to answer the questions about polyatomic ions frequently enough that you'll become familiar with them because you'll use the chart over and over and over. Okay?
Okay.
All right. So, looking at our polyatomic ions, we can think about the charge that will be on a given polyatomic ion, even if we don't have the chart. All right. So this chart, like I said, doesn't include all of the polyatomic ions. All right. And in this case, PTO4, which they are calling the platinate ion, isn't on our polyatomic ion chart. But we don't need it to be on our polyatomic ion chart because we can know information about it simply by the name of the compound and also looking at the combination of the ions in the compound. So we have this compound, and they say that the name of it is iron 3 platinate. Iron 3 platinate. Now that 3, do you know what that 3 means in iron 3 platinate?
No.
The 3 is telling us about the iron ion. You know what it's telling us about it?
No.
Well, where is iron? What element is iron?
Number 26.
That's right. Iron is number 26. So iron is a transition metal, and it can form multiple kinds of ions. It can form +2, +3, and maybe even other kinds of ions, usually just +2 or +3. But it's not completely uncommon to hear transition metals forming crazy kinds of ions. Okay? So, when we combine iron with our unknown polyatomic ion, we need some information about the kind of iron that we have here.
Oh, and that 3 is telling us
That's right. That 3 is telling us,
that there's 3 platinates?
no, it's not telling us that there's 3 platinates. It's telling us that there's a +3 charge on the ions in this iron 3 platinate. So that 3 is telling us that it's iron 3, or iron with a +3 charge. Okay? So the irons in the platinate has a +3 charge. Okay? So this compound here, rubidium platinate, all right, what do we know about rubidium? That's element 37.
Oh, if it's in the first row, it has to have a +1 charge.
That's right. It has to have a +1 charge. So what does that tell us about the platinates?
I don't know.
Well, apparently, one of these PTO4s is all you need for 3 rubidiums. So what does that tell us the charge is on the platinate?
Oh, it must be let's see, a -3. -3, so that you need 3 rubidiums with a +1 charge.
That's right. Very good. So if this is a -3 and the iron is a +3, then what is the ratio going to need to be?
If the iron's a +3 and the platinate is a -3, is that what we said?
Yeah. So PTO4 3 minus.
How did you know it was a -3?
Well, because we saw that in the other compound they provided with rubidium, 3 rubidium.
Oh yeah, 3 rubidiums were needed, 3, and each one had a +1 charge.
That's right. Good job. So, what do we know about our resulting compound?
It's got to be C.
C?
Yeah,
How did you know?
because you need only 1 iron 3 for 1 platinate with a 3- charge.
Okay, very good. So what we learned there is even without the polyatomic ion table, we can know the charge on some of our polyatomic ions simply by knowing about what we call counter ion, the other ion that is with it. We also learned that to help us differentiate between the charges that can be on transition metal ions, we use a Roman numeral here to tell us the charge that's on that ion. So we can use the periodic table to know the charges on the first 2 rows, but our transition metals, it's not clear, and so we use a number to help us know what the charge is. All right. So what metal would be a reasonable candidate to replace the XPO4, the X in this XPO4 compound, XPO4? So if this is an ionic compound, let's see if we can use our polyatomic ion table here. Polyatomic ion table is on the back of your periodic table, right? And here it is. Can you find on there the PO4 ion, what its name is and what the charge has on it?
Oh, there it is. Phosphate. Phosphate ion. PO4 is the phosphate ion.
Very good. And what kind of a charge does it have?
A minus charge.
Okay, whenever I ask for what kind of charge it is, you always have to say what the number and the charge.
So it's a 3- charge?
That's right, 3- charge. And you can say -3 is okay too. All right, so what does that tell us? That must be on the charge of the X ion here.
I don't know.
Well, there's only one X for every PO4.
Oh, so it's got to be a +3?
That's right. X has to be a +3. So let's think about which one of these elements could result in a +3 charge. Oh my goodness, my goodness, my goodness. All right, so magnesium. Magnesium's here. What kind of a charge is it going to be?
It's not A because magnesium would be a +2. It's not B. It's not C. Those are all +1. Scandium. Where's SC? Where's SC?
There it is. It's element 21.
Oh, scandium. Okay. So it's a transition metal. It might be a +3. Let's see. What's the last one? SR. What's that?
That's strontium. That's right here, 38.
Strontium. Okay, so that's just a +2. So it can't be A, B, C, or E. So, and scandium is transition metal, so it could be D.
That's right. That's right. D would be a reasonable metal because it could be a +3 charge as a transition metal. All right, very good. This stock system of naming ionic compounds is used when we're using a transition metal. So like we saw, if you ever have a transition metal and you need to help the person know what the charge is on the transition metal ion, then you can use the Roman numeral to tell people what the name is on that period, on that transition metal ion. Also, binary molecules. Now the word binary means there's only 2 different kinds of elements. Binary molecules, the ending of our oxygen, nitrogen, phosphorus, chlorine, right, always goes to ide. Nitride, phosphide, chloride, iodide. And we already mentioned that as well, right? All right, very good. Now, what about naming covalent compounds? Now, a covalent compounds is another name for a molecular compound. Okay? Molecular compounds are, well, do you remember, how do we tell what a molecular compound is, or whether a compound is molecular or not?
I can't remember.
Well, how do we know if a compound is an ionic compound?
It has a metal or it's made of ions.
That's right.
Oh yeah, I remember. A molecular compound is only made of non-metals.
That's right. And our non-metals are here.
On the right of the staircase.
That's right. On the right of the staircase here are our non-metals. Very good. Now, when we name molecular compounds, we use the prefixes, the Greek prefixes a lot. So we're going to kind of review them a little bit. Monodiene tri, I think everybody remembers. Hexa, penta, pentagon, hexagon, I think people remember those two as well. Octa, octopus. Nona, might not be as easy to remember. Deca stands for decade or decimal. Remind us that it means 10. Tetra is kind of a hard one to remember. Did you ever play the game Tetris?
Yeah, but my thumbs don't work really good, so I usually don't play it.
Oh yeah, but Tetris, in the game Tetris, it's about 4s, right? The blocks always have 4 units, and in the end, if you get all 4 lines at once, it's called Tetris, right? So tetra is our reference for 4, Tetris. Hepta is 7, and nona is 9. And the way that I like to remember these is through the calendar, because September comes from a similar prefix as hepta does, because September used to be the 7th month, just like October used to be the 8th month, and November used to be the 9th month. But they added in a couple months when we decided we didn't want to do 10-month calendar anymore, we wanted to do 12-month calendar. So that helps me remember that September is the 7th month, November is the 9th month. Okay? So we use these prefixes when we're naming a compounds. So for example, hydrogen chloride, what elements do you think are in hydrogen chloride?
Hydrogen and chlorine.
That's right, hydrogen chloride, HCl. So we don't have to say monohydrogen monochloride if there's just one. You can just say hydrogen chloride. What about phosphorus pentachloride? What two elements?
Phosphorus and chloride. What's the letter for phosphorus again?
Let's see the symbol for phosphorus. There it is, 15. 15, so it's P.
So it's PCl, and the penta means 5. So P, let's see. Is the penta going for the chloride or the phosphorus?
The penta is attached to the chloride there, so it goes for the chloride. So it's P.
Cl5?
That's right, PCl5. All right, what about this one? Tri-Selenium Dinitride. Here's selenium, Se, number 34. Here's nitrogen, number 7.
Se3N2.
Very good, Se3N2. Tri-Selenium Dinitride. Now, notice all of these compounds, are they molecular or ionic?
Molecular.
That's right, and because they're molecular, that's why we're naming them this way. We name them with the mono, di, and tri. If it's ionic, we don't name it that way. We don't need to, because we can tell if I call it, for example, magnesium bromide, we know that there's magnesium and bromine. We know that magnesium only forms a +2 charge because of its location. So simply by saying magnesium bromide, everybody will know what it is. If it's a transition metal, and I say, for example, cobalt chloride, then I'll say cobalt 2 chloride because it's a transition metal, and that'll help somebody or people remember or know which ion of cobalt I'm talking about. Okay? So with our binary compounds, we use the mono, dis, and tris. The mono is pretty much always eliminated except for something like carbon monoxide, right? You've heard of carbon monoxide.
And carbon dioxide. Yeah, they're carbon dioxide.
Yeah. So that shows us a good example of why we need to have these prefixes when naming molecular compounds, because there's multiple ways in which these nonmetals can come together, but not for ionic compounds. Representative metals, ionic compounds, and remember the representative metals are our first 2 and our last 6 here. Ionic compounds made of representative elements always follow the same pattern in terms of valency. Metals always lose electrons and nonmetals always gain electrons. Okay? And sometimes you'll see like carbon monoxide, right? We don't have to put the O twice, so there's some conjuncting of vowels in there. All right, SCl2. Let's see, tell me, is that a molecular or ionic compound?
Can I see the periodic table?
Yeah, so
Where's S?
it's number 16.
Okay. Oh, and Cl's right next to it. So this is a molecular compound. What was the other name for molecular?
Oh, covalent. Covalent is another name.
Okay, so molecular compound, sulfur, I'm going to use the prefixes because it's molecular, sulfur dichloride.
Very good, sulfur dichloride.
And the next one's hydrogen fluoride.
Very good.
And the next one's dinitrogen pentaoxide.
Very good. Good job. So the dinitrogen pentaoxide, all of these were these molecular or ionic compounds.
These are all molecular, no metals in there.
Very good. Excellent. So what's the correct formula for nitrogen triiodide?
Nitrogen triiodide, 3-iodide. That's B, nitrogen triiodide.
Very good. Nitrogen triiodide. What about P4O10?
That was tetris or tetra. 10 is decade, tetra and decade, tetra, phosphorus, tetra. So B.
Very good. Tetraphosphorus dicoxide. All right. Now this is a little flow chart that might be helpful for naming compounds. I don't find it terribly helpful, but it's in the book, and it's interesting to look at maybe once or twice in your life, and then you can pretty much get it in your mind easily enough. We're also going to have just a brief conversation here about carbon compounds. carbon, if you look at where it's at on the periodic table, right, would you say it wants to gain electrons or lose electrons?
It wants to gain electrons.
Okay, so if it gained how many?
4.
If it gained 4 electrons, it could have what we call a noble gas electron configuration. But look, it could also lose 4 electrons. And then it also has a noble gas configuration. So it becomes an interesting scenario here. Carbon can either gain or lose electron density when it reacts with other elements. And so it makes it an extremely diverse element. And the compounds that it can make are, some say infinite. Lots and lots of ways that carbon can come together. So, we have a whole other class to talk about carbon compounds. You know what it's called?
No.
Organic chemistry.
Oh, no, organic. I've heard all about organic.
Yeah, organic chemistry. It's not a bad class. It's a fun class, but it talks about very complex, or not complex, but the complexities of carbon chemistry. So when you have a carbon compound that contains 1 carbon, then the prefix meth is used, as in the case of methane. 2 carbons, eth, 3 prop, 4 bute. And those are slightly different. Meth, eth, prop, and bute, 1, 2, 3, and 4. They're slightly different than our Greek prefixes that we mentioned for naming nonmetals. Penta, hexa, hepta, nona, and deca, they're all the same. So that's not different for naming what we call alkanes or carbon-containing compounds. But just a brief awareness, you'll see these names as we mentioned some common names like ethanol. I think you probably have heard of ethanol before, or isopropanol, right? Some common names. Okay, so let's see if we can name these compounds here.
Me?
Yeah, you. What is the name of this compound here?
Can you give me the periodic table?
Yeah, there we go.
Okay, so that's a sodium ion with oxide ion. So that is going to be, they're both representative elements. It's an ionic compound, so I think I could just call it sodium oxide.
That's right, sodium oxide. We don't need the di or the tri, just a regular old ionic compound.
And the next one is the same, potassium oxide.
Very good. Not potassium, dipotassium oxide, anything like that, because it's still just an ionic compound. Okay, this next one.
No clue.
All right, so we need to bring in the big guns. We need to bring in our polyatomic ion chart. So I have the polyatomic ion chart over here. We bring it in, and we can see if any of our ionic polyatomic ions are being used. Let me try to focus in here a little bit. Okay, there we go. See if any of our polyatomic ions are being used in this compound.
Oh yeah, there it is at the top. Ammonium.
NH4, that's right, is ammonium.
Oh yeah, and then ClO3 is near the, well, yeah, right there. Chlorate. So what does that mean?
Well, we would just name this ammonium chlorate, just like that, okay? So we used our polyatomic ions chart to tell us what the names of those polyatomic ions were.
Okay, good.
How about this last one?
Mg is magnesium, right?
That's right, very good. Mg is magnesium, but I'll bet you don't know what this is.
No, I don't.
So we use our polyatomic ion chart.
I don't see it on there. It's not on there.
C2H3O2.
Oh, there it is, yeah.
Yeah, right here, see?
Yeah, so magnesium and acetate. Magnesium acetate?
That's right, magnesium acetate. Very good.
Okay, that last one, the next one is Cr. What's the periodic table? I can't remember what Cr is.
So here's our periodic table. It's element 24. Can you see it?
No. Oh, chromium?
Yeah, chromium.
Okay, chromium oxide.
Very good, chromium oxide, but you're missing something.
Chromium and oxide. Oh, because chromium is a transition metal, it's in the blue there, I got to tell people what the charge is on the chromium ion. How can I tell what the charge is on the chromium ion?
That's right. We have to name this either chromium 2, chromium 3, chromium 4, something like that, based on what the charge is on the chromium ion. But how can we tell? Well, what we can do is we can use the crisscross rule backwards and see what the charge is on the ion. So can you tell what it is if you do that?
Yeah, chromium is going to have a +3, oxygen is going to have the -2, so it's going to be chromium 3 oxide.
Very good. Chromium 3 oxide. Excellent. And the last one there?
Where's Zn?
Right here?
Oh, zinc?
Yeah.
Okay, so Zn, zinc, oxygen, oxide, or no, bromide. Zinc bromide. Bromide has a +2 charge. So zinc 2 bromide.
All right, so you put a number with it. Why did you decide to put a number with the zinc?
Because it's a transition metal.
That's right. Very good. Zinc 2 bromide. Now, it turns out that zinc doesn't have any other charges it can form. It only forms a +2. So people only call it zinc bromide. But in this class, if you call it zinc 2 bromide, I'm perfectly okay with that. All right, let's see here. These last couple of elements to name. Or I guess we want the chemical formula for these ones, right? Can you do it? What's the first one?
Chemical formula. Calcium is Ca. I don't know which element hydroxide is.
It's because it's probably not here, right? We have to remember now.
Oh, yeah.
Yeah, so we sometimes have our polyatomic ions to take into account. So here's your hydroxide ion.
Oh, yeah. Hydroxide's a -1 charge.
That's right, and that's what you need to do when you look at your polyatomic ion chart. You need to always look at the name of the polyatomic ion and then the charge. What is the charge going to be on the calcium ion?
Calcium, where's that at?
Element 20.
Okay, so it's going to be a +2. Hydroxide's a -1. So I would say the chemical formula is CaOH, but then you got the OH in, you got 2 of them. That's a polyatomic ion, so it's going to be like CaOH2. Oh yeah, and then the parentheses like that.
Okay, very good. Right, so the parentheses are used to help us recognize that we're having 2 of those polyatomic ions. Okay, very good. How about copper 2 chloride?
I remember chloride. Chloride is halogen, so it's just a -1. So if it's copper 2, that 2 is telling me that the copper is a +2 charge. So it's going to be Cu, and if the Cu has a +2 charge, the chloride has a -1. CuCl2.
Okay, very good. So again, kind of the balancing out those ions, right? Copper has a +2 charge. There's going to need to be 2 chloride ions. All right, what's this last one here?
Those are polyatomic ions, I think. Can you bring up that polyatomic ion chart? Ammonium, that's at the top, ammonium, phosphate. Where's the phosphate ion? I don't see the phosphate ion. Oh, there it is, it's on the bottom.
Right, down here. PO4, 3-.
3-, and the ammonium is a +1, so you're going to need 3 ammoniums for every 1 phosphate. So it's NH4, it's in parentheses, there's 3 of them, and then there's the phosphate.
Very good, that's the chemical formula. All right, now let's remind ourselves how to name hydrides. Let's see if you can remember how to name hydrides.
Ca, that's calcium, SO4, I don't know. What's the polyatomic ion chart say? Sulfate, there it is, sulfate ion, SO4, 2-. Calcium, can you bring up the periodic table again? Calcium, oh, there it is, okay. Calcium has a +2, and the sulfate has a -2. So, I guess I didn't need to know that, did I?
No, but we just know that this chemical's name is what?
Calcium sulfate.
And then what do we do here?
I can't remember.
Well, we just use our prefix and say hydrate, right? So what's the prefix for 2?
Di.
That's right. So this is calcium sulfate dihydrate.
Okay. So we got cobalt. Cobalt chloride hexahydrate.
Very good.
Oh yeah, and then the 2. I forgot the 2. So yeah, we knew the 2 because how?
Oh, because there's 2 chlorines and chlorine has a -1. That 2 isn't saying that there's 2 chlorines, remember. 2 is saying that the cobalt has a +2 charge.
Okay, right. So the last one is iron iodine. What is iodine's charge? Can I see the periodic table? Okay, so it's going to want to do a -1 charge. So if there's 3 needed for the iron, that means it's iron 3 iodine goes to iodide. Iron 3 iodide trihydrate. Iron 3 iodide trihydrate.
Very good. Excellent work. All right, here's a little tricky one now. What is the correct name for Cu2S?
Is it copper 2 sulfide?
Copper 2 sulfide? What made you think that?
Well, because there's 2 coppers and 1 sulfide.
Okay, not quite. What's wrong with that?
I don't know.
So why is it called copper 1 sulfide?
Copper 1. There's 2 coppers. It should be copper 2 sulfide.
But the 2 there, when I say, or this 1 here, when I say copper 1, what is that telling me? Is that telling me that I have 1 sulfur or 1 copper?
Oh, no. No, it tells you the charge. So if it's copper 1, that means the charge is +1. And sulfide, what is sulfide again?
Here, let's look on the periodic table. Here's sulfur. So it's going to want to have a -2 charge. Okay?
Yeah. Okay, so -2 and copper is a +1. So yeah, you're going to need 2 coppers with a +1 charge. But it's still called copper 1 sulfide.
Excellent job. Excellent job. All right, and ammonium sulfate.
Ammonium. I remember ammonium, NH4.
All right. And sulfate, do you remember that?
No,
Look at the polyatomic ion chart here. See if you can find it.
I don't see it. Oh, there it is. Sulfate -2 charge. So you're going to need 2 ammoniums, and then, so the answer is D.
All right. Excellent job. So you're learning how to name. You're learning how to name ionic compounds, molecular compounds, ionic compounds that contain transition metals, all sorts of good stuff. Okay, good job. Done with the chapter. Talk to you later.
Bye.